Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, good afternoon, everyone. Welcome to the talk. It's my great pleasure to introduce Bozo Bonadapur. I hope I pronounce it right. So, he's a research assistant professor from University of Waterloo. He is broadly interested in the correctness of software development using formal methods, especially in the area of distributed and embedded real-time systems. So today he's going to share with us his work on the model-based code generation and debugging of concurrent programs.
Okay, thank you very much for the introduction and your kind invitation. So, as Yuxiang said, I have been working on not necessarily software, but system correctness for since I became a graduate student. This talk will focus on model-based code generation, which basically focuses on correctness by construction. So let me give you an overview of the long-term vision that I have, at least for the next few years. So I'm generally interested in program correctness, and I'm basically following two lines of research. One is offline, or pre-compile time, and one is online. So by offline, I mean correctness by verification, correctness by construction. I've done some work on compositional verification. And correct by construction is what I'm more interested in. So at what I call it micro level, I'm interested in model repair and model synthesis, where given an existing model and a set of properties, the problem is how we can fix bugs and fix errors in that model. But what I call it at a more macro level is model-based code generation, where there exists code and we want to transform it to different types of workable platforms. And recently, I've been working on tracing and runtime verification because of all the limitations that we all know that state-level synthesis and model checking have. There is now an emerging trend on using runtime verification and tracing for debugging purposes. So this has been my fascination more recently. I gave a talk here at MSR in 2008, early 2008, on model repair, and today I'm going to talk about model-based code generation and a little bit about tracing and debugging. So the first part is on model-based construction of distributed programs, and this is a joint work with Marius Bozga, Mohamed Jaber, Jean Kilboff, and Joseph Sifakis. So the work goes back to my postdoc time at Verimag, and I'm still collaborating with them. So that's been fun. So the idea here is we want to start from a high-level model and generate code from that high-level model. But the high-level model may be associated with with code as well. So let me describe in more detail. Why do we do model-based software development? I think you're all familiar with the reasons. Because they abstract implementation details. Analysis of models is easier. We can do levels of verification, model checking on model, whereas that's more difficult to do at implementation level. We can do testing, simulation, and all sorts of procedures that ensure model correctness. And then we can transform the model into actual implementation. But the fact is, during this transformation, when it is done manually, the bugs are introduced by programmers, because it's a human process, it's a manual process, and bugs are inevitably introduced. So in distributed systems, I would argue that the problem is a little bit more amplified when we develop software because of the inherent complex structure of distributed systems, because of concurrency, non-determinism, race conditions, low atomicity, the issue of faults. So basically in distributed systems, the problem is a little bit more difficult, and the gap between developing models and implementing and deploying software is I would argue is a little bit wider. So when I joined Verimag, it was in the early stages of a framework which is called BIP. I would like to emphasize that I'm not religious to this framework in any ways, but it's just one way to deal with the problem. My slides are, I think, I'll cut a little bit from the bottom and the top, but that should be fine. So the idea is that we start from a high-level model, and I will say what I mean by a high-level model. And in the high-level model, we can use verification tools such as the dfinder tool that's been developed at Verimag for finding deadlock states in a compositional fashion. And then there are some performance, for instance, criteria involved. Then we do some source-to-source transformations, for instance, to get more close to distributed computing, reality, for instance, point-to-point message passing and things like that, and then we generate code. So this is the part that I'm going to talk about today, from the system model BIP to then source transformation and then eventually code generation. So the philosophy of this framework is that we want to have different programming paradigms, such as data flow, event-driven, synchronous, and so on. And we want to follow a principle of constructivity, which means that if low-level components satisfy a set of properties, then by composing them, we want to preserve those properties. Of course, this is a hard problem. We cannot solve it in all cases, but for some safety and some liveness properties, that can be done. And then from this high-level model, we want to do model transformation and then get implementation that is correct by construction, by preserving functional properties and some extra functional properties that I will talk about. So this is the sort of the outline of the first part of the talk. Let me first start by describing the global state semantics of BIP. So basically, a model has 3 layers. The first layer is the layer that we describe the behavior of the model. So these are the set of components. And each component is basically a state transition system or a Petri net. And each transition in each component can be associated with a C++ function. Then there is a level of interactions, which is basically a set of synchronization primitives, such as rendezvous, broadcasts, and so on. And there can be priorities for scheduling purposes, which basically means if 2 interactions are enabled at the same time, we can give priority to one. There is composition going on. So if we have a composite component here and another one right here, then we can compose them by another set of interactions and priorities. And we can get basically a new component that can be composed with other components later. Let me show a very simple example. We have 4 components here. We intend to have the first component as a sender. The rest of them are receivers. There's only 2 transitions, 1 transition and 2 states. This transition is labeled by S, and it is associated with a port S, R1, R2, and R3. We compose them by the interaction S, R1, R2, R3. That means when all of these ports are enabled, then this interaction can take place, and each component takes a transition from the first state to the second state. So when all these components are at their initial state on top, this interaction is enabled because S is enabled here, R1 is enabled here, and R2 is enabled here, R3 here. and therefore the transitions can be taken locally, and the components will reach the second state. Let's imagine we don't have any priorities. We actually have just one interaction, so priorities don't. A priority doesn't make sense anyways. And this would be a rendezvous interaction. And that's how we show it graphically. Now the same components, but with a different interaction. So this interaction says that if S is enabled, or S and R1, or S and R2, and all the way to the end, which is the last one is S and R1 and R2 and R3, then the local components can make their move based on the ports enabled here. So this is basically a broadcast, and it gives priority to the larger interaction. So when all of these components are in their initial state, the maximal interaction is going to be S, R1, R2, R3. So that is basically a broadcast. And that's how we show a broadcast graphically. So you can come up with more interesting types of interactions. For instance, the upper one is an atomic broadcast, which means that when A sends a message, then either B and C both receive it, or none of them. And the bottom one is a causal chain. So when A is enabled, then the interaction would causally go downwards here. So I was not involved in this part of the work, but it has been shown that this framework gives expressiveness more than any existing process algebra. So that was the basic semantics in very simple words. So when I joined the effort, we wanted to take such models and then generate distributed code. And by distributed code, I mean that each component that I showed becomes one standalone application, and the interaction basically becomes a synchronization primitive. And then the question is, how do we generate distributed code out of multi-party interactions? If it is only binary interaction, that is easy, because most existing networks, they provide primitives for point-to-point message passing. But when we have multi-party interactions, the problem becomes a little bit more difficult. So I started the effort by doing a case study. And that was distributed reset, which is a very well-known algorithm in self-stabilizing systems due to Arrow and Gouda. I'm going to describe the algorithm very quickly in a high-level fashion. The algorithm has 3 layers. There is an application layer, and the goal is we want to achieve a distributed reset. A process initiates a reset, and then the whole system is supposed to get reset. There is an application layer. There is a wave layer, which performs diffusing computation. And there is a tree layer, which maintains a spanning tree throughout the network. Let me just focus on the middle layer here, the wave layer, which is a diffusing computation. The algorithm is very simple. A node, such as, let's say, 4, requests a reset, a global reset. It sends a message to its parent, 1. 1 sends the message to its parent, 0, which is the root. Then when the root receives this message, it resets its own state. Then it bounces back, sends a message to its children, 1 and 2. The same thing goes on until we reach the leaves. Then when all the leaf children of a node are reset, then they start the completion wave. For instance, 7 is the only child of 4. It sends a message to 4. The same thing between 3 and 1, and the same thing between 8 and 6, and the same thing between 5 and 2. So in the first wave of completion, 3, 7, and 8, which are the leaves, are complete. Then their parents. And now, since these 2 are complete, 2 and 1 become complete, and then all the way back to the root, and the diffusing computation is complete. It's a very simple algorithm. A self-stabilizing version of this algorithm is shown by these 4 or 5, 1, 2, 3, 4, 5 innocent-looking guarded commands. By self-stabilizing, I mean that starting from any state, that's the Dijkstra's notion of self-stabilization. So by starting from any state, doesn't have to be reachable, any state of the system, the diffusing computation is complete within a finite number of steps. So that means that it takes care of faults as well. So the algorithm was very easy. This is now a little bit more complex. And now I'm going to develop a model for that in our framework. So I introduced 3 states, normal, init, and reset. We go from normal to init. This is only for one component. If a node receives a request, it resets its state when its parent says to do so, and then it completes. There are some self loops going on here to make sure that multiple sessions of reset can go on safely. Of course, faults, these would be the ports. Faults can happen. That means it can change the state of the system randomly. It can change the session number of a component. And these would be the recovery transitions. I'm not going through the details, so don't worry about the details. What I'm going to do is I'm going to freak you out by the level of details here. And these would be the ports. So from that pictorial description that I gave you of the tree, which was very comprehensible, easy, then to guarded commands, and now to this, what I call almost a mess, you can see how things get complex and complicated from a high-level description to a lower level of formalism, right? So then I would argue that let's stop here and not go through, developing distributed code. Now this is one component. The interaction level of these components would be complex too, because at development time, we don't know which components are going to interact with each other. We don't know which components are going to be parent and child to each other. So we have to develop, this the complex type of interactions to make sure that we capture all types of parent-child relationships at runtime. Now imagine we ask a programmer to develop a program using, say, socket programming to implement this algorithm. Although the algorithm is very simple, it's going to be difficult to anticipate all types of synchronization and to guarantee correctness. So the goal is to stay at this level of abstraction and then generate code, distributed code. So in action, a BIP model is orchestrated by an engine or a scheduler, and this engine or scheduler can be centralized or distributed. And my focus is going to be how we develop a distributed scheduler for during code generation for this type of models. Okay, so the next step of my talk is about transforming a high-level BIP model into an intermediate model where we don't have multi-party interactions and we have partial state semantics. So let's say what I mean by partial state semantics. Let's imagine this is a very simple BIP model. There are 7 components here. There is interaction I1, I2, and I3. Now let's imagine I1 is enabled. That means these 3 components, they start executing code. And let's imagine that C3 finishes first. That means C3 is available for computation. C4 is also available for computation. That means I2 is enabled. And that means, again, C3 and C4 can run concurrently, right? So there is an issue of atomicity here. In the high-level model, either I1 or I2 could execute. But when we go to a concurrent setting, I1 and I2, depending upon enabledness of components C3 and C4, I1 and I2 could run concurrently. So then the question is, how do we manage atomicity in the sense that the concurrent implementation adheres with the high-level description of the model? So let me give a more concrete example. This is the high-level model, 4 components and these 3 interactions, alpha 1, alpha 2, and alpha 3. Now, if we assign an engine or a scheduler to manage interactions alpha 1 and alpha 2, and another one to manage interaction alpha 3, these components, these 4 components are replaced here. That means when alpha 2 and alpha 3 are enabled, this component sends a message to this engine and says this port is enabled. The same thing happens for these 2 components. And then both alpha 2 and alpha 3 are enabled, and they send a message back to these components that they can execute alpha 2 and alpha 3 and their associated transitions locally. But then the problem is, how would we guarantee that this doesn't violate the semantics of the original model? On top of that, there is the issue of conflicting interactions. So what if we have interaction alpha 1 and alpha 2 that share port P? Obviously, we cannot execute both at the same time because there is only one transition here enabled, which is labeled by P. So both interactions cannot be executed. There is another type of conflict. What if we are at this state? That means this transition is enabled. This transition is also enabled. And if this so that means potentially these 2 interactions alpha 1 and alpha 2 can be enabled, but this component can take only one of these transitions at a time, right? Then the question is, how do we resolve this type of conflicts if we are in a distributed setting? In a centralized setting, it's easy. All these enablednesses are sent to the scheduler. The scheduler atomically decides which interaction should go forward. That is straightforward, but in a distributed setting, that's going to be a little bit more difficult. So, sure.
The conflict is defined by whom?
You can find out where potentially could be conflicts by doing a very simple static analysis. Because let me go back here. So if you have a model like this, then by looking at this, I know that starting from this state, both transitions P and Q could be are enabled. And if this port and this port here are also enabled, that means alpha 1 and alpha 2 are concurrently enabled. But this component can only take one of these transitions. And if these 2 interactions are managed by 2 different engines, they sort of have to coordinate at runtime and let this component know that either alpha 1 or alpha 2 exclusively are enabled, and therefore only one of these transitions are taken, right? So a simple static analysis finds out where the conflicts are. Or I should say potential conflicts. Okay, so here's a short story. When I started working on this problem, I developed an algorithm. Actually, it was a very simple algorithm. It was a very naive algorithm, but still, it was an algorithm. It worked. We did some experiments. It was fun. And then I was just browsing one of the books that I really like by Chandy and Misra. It's one of the God books. And I bumped into this problem, which is called the committee coordination problem. And that was only by chance. Professors, and this is quote unquote, professors in a certain university have organized themselves into committees. Each committee has an unchanging membership roster of 1 or more professors. From time to time, a professor may decide to attend a committee meeting. It starts waiting and remains waiting until a meeting of a committee of which it is a member is started. All meetings terminate in finite time. The restrictions on convening a meeting are as follows. Synchronization: meeting of a committee may be started only if all members of that committee are waiting. And exclusion is no two committees may convene simultaneously if they have a common member. And the problem is to ensure that if all members of a committee are waiting, then a meeting involving some member of this committee is convened, which is a progress property. This is exactly our problem. A committee is an interaction. A professor is a component. If two committees, that means two interactions that share one component, are enabled at the same time, only one should convene, right? So that was exciting. So this problem was introduced back in '88, and I thought there should be a long line of research doing all sorts of, introducing all sorts of committee coordination algorithms. So I started doing a survey on the literature. As I said, the problem was introduced in '88. And the solution was given by reducing this committee coordination problem to distributed dining or drinking philosophers problem. In '89, Rajiv Bagrodia introduced another solution based on message counts and ensured synchronization by a reduction again to dining and drinking philosophers problem. And he presented some simulations, and then in 1990, the whole thing dies. There is absolutely nothing happening on this problem after 1990. I have no idea why. Maybe the closest language to what we are doing is Ada. And so I think Ada would be the only language that could use committee coordination, and because of all reasons that Ada was not as popular as imperative languages, other imperative languages. There was no research on this problem. So now, reviving the committee coordination problem, there are all sorts of questions that maybe did not make a lot of sense back in the 80s. One of them is, how do we guarantee maximal or maximum concurrency? Because if we want to generate code and then deploy a model, we want to have as much as parallelism as we can, right? So maximal concurrency is a problem. Fairness. This is another problem. So these are all the problems that have not been addressed very in detail. Fault tolerance or self-stabilization, waiting time, service time, and the last one, which I cannot see, the effect of time. I think this is the utilization. So these are all the problems that have not been addressed. So there is going to be a lot of opportunities to do research on solving different types of committee coordination problems. So some of the results that we developed are, these are the impossibility results. Maximal concurrency in the presence of an unfair scheduler is impossible. Impossible in distributed computing community means that we cannot develop an algorithm that guarantees maximal concurrency if we have an unfair scheduler. Providing maximal concurrency and committee fairness even in the presence of a fair scheduler is impossible. Maximal concurrency and bounded waiting time satisfying both is going to be impossible. So that's one side of the story, developing committee coordination algorithms. The other side is how can we transform a high-level model using committee coordination solutions in a structured manner and then generate code? Because one can develop an ad hoc solution that starts from a high-level model, uses some committee coordination problem, and then generate code. But that's not going to be very efficient, and I will back it up by some experimental results, because different committee coordination algorithms will end in completely different experimental results. So the first solution that I was talking about before I discovered there exists a problem called committee coordination was to assign an engine to a set of conflicting interactions. So for instance, in this case, if this is our high-level model, and alpha 1 conflicts with alpha 2, and it conflicts with alpha 3, and the same thing for alpha 4, 5, and 6, then what we are going to do is we assign one engine to these three, which resolves all the conflicts between these three locally. And there will be another engine which resolves all the conflicts between these three. So again, these are the components. And there will be one engine that manages alpha 1, 2, and 3. And there will be another engine that resolves the conflicts between alpha 4, 5, and 6. And these two engines do not have to talk to each other, because there is no cross conflict between these two engines. So that was a very straightforward solution. The implementation of an engine is done by a PetriNet, and let's not worry about the details of this PetriNet, but basically the PetriNet, in this PetriNet, this is where we receive a message of if a transition is enabled from a low-level component here. And when all the ports of an interaction, for instance, alpha 1 is enabled, then the token is passed through this barrier here. One of the preliminary experiments that we did was on bitonic sorting. And the reason that we were able to do that was this is a high-level description of bitonic sorting, and all these interactions here are non-conflicting. And this is how the model looks like by inserting those engines. These are the interactions that are managed by these engines here. Let's not worry about the details of how the transformation is done, because I will talk about the transformations in more detail after these results. So these are some numbers of bitonic sorting with different sizes of arrays for sorting in parallel. This is an MPI handwritten code. So for instance, for the 20K size array, it takes 80 seconds. Our implementation based on TCP sockets takes, or I should say implementation and transformation, takes 96 seconds. Obviously, it has more overhead. That is expected. Then what we did was we developed a direct transformation from a high-level model to an implementation using MPI. The strange thing here is our transformation takes less time than a handwritten code. So, I mean, this was very strange, because an automated generated code is now performing better than handwritten code, which didn't make a lot of sense. So when we dig into the problem, we realized that we are using collective send and receive primitives in our transformation, whereas when we develop the handwritten code here, it uses the regular send receive primitives in MPI. So this happened to be faster. Of course, if we use the same type of primitives here, it's going to behave similarly. Now, the first one was in case of one CPU. This is 4 CPUs, and this one is 4 CPUs on 4 different machines. So this was a multi-core implementation, and this was a distributed implementation. So if we ignore this column, the overhead is less than 50%. And the fact is, our focus was not really on performance evaluation. Our focus was more on the issue of correctness. But obviously, if we want to take this to a more serious step, we have to take into account performance issues, and that's one of the things that I'm hoping to achieve by my visit here, because Yuxiang is an expert in parallel computing. All right, so the problem with that simple solution was that if we manage all the conflicting interactions by one engine is in some models it can be the case that all the interactions are conflicting, such as this one. These all share the same port. So the first interaction conflicts with the second one with the third one with the fourth, and all the way to the end. So if we take that approach, that means we have to manage all the interactions by one engine, which is a totally centralized solution. And then the question is, how can we add to the level of parallelism and have distributed engines, but at the same time we resolve the conflicts safely. So then we go back to committee coordination problem. Now what I'm going to show you in the next few slides is there can potentially be completely different solutions to committee coordination. Let's only focus on binary interactions. And if we take only binary interactions, committee coordination is going to be almost the same as the matching problem in graphs. In matching, we are looking for a set of edges that do not share a common vertex, right? So for instance, in this graph, this is a matching because it's an edge that does not, there's no other edge, so there's no conflict. This is also a matching, that the red vertex here and the red edge here and here, because they do not share a common vertex, and the same thing here, right? So that could be one potential solution for binary interactions. I'm now going to show another variation. Let's imagine this is my high-level model. What I'm going to do is I'm going to represent each conflict, for instance, between I1 and I2 by one vertex. So there is conflict between I1 and I2. This is this. Okay, maybe I should rephrase that. I'm going to represent each interaction by one vertex. And I'm going to show each conflict by an edge between these two vertices. So I1 conflicts with I2. There is this edge between I1 and I2. I2 conflicts with I3, and I add this edge between I2 and I3. It's a reduction, basically, to solve the problem. Now, if I solve the independent set problem for this graph, I'm basically solving the conflict resolution problem. The independent set problem, the solution would be either I1 and I3 or I2. That's another solution. Now I can translate this to also finding a clique. If this is my high-level model, I'm going to, again, represent each interaction by a vertex, and I connect this vertex to all non-conflicting interactions. So I1 does not conflict with I7, I6, and I4, and this is what I get. I do the same thing for other interactions. Now, if I find the clique, or the maximum subgraph, the largest subgraph, then I'm basically finding the maximum size of interactions that can run concurrently. So 3 different approaches to solve the same problem. So, my point here is to solve the same problem, we can take completely different approaches. And then what I'm going to show you is by taking different approaches, we get completely different performances for the same experiment or the same benchmark. So now the other aspect of the problem is we want to develop some type of transformation where we can embed different solutions to the committee coordination problem in a plug-and-play fashion. So what we developed was a 3-layer architecture as follows. Let's imagine this is the high-level model. And we take as input a partition of interactions. So the first class, or the first set here, is alpha 1 and alpha 2. The second set is alpha 3 and alpha 4. This is the input. And this is given by the designer. We replace each of these components by the same component with the same name here, but the structure is going to be a little bit different. I don't go through the details of how we have to change the internal structure to make sure that we have partial state semantics. But let me just say that each component is now going to have two ports. One is the offer port, which means that which transition is enabled. So the intention of this port is to send a message to the scheduler. And this port, which is called port, is intended to receive a notification to execute a transition. So that's the first layer. The second layer is a layer that which we call it interaction protocol. So the interaction protocol resolves local conflicts internally. It also receives from each component which ports are enabled. If it can resolve a conflict internally, for instance, the one between alpha 2 and alpha 1 here, or the conflict between alpha 3 and alpha 4 here, then it does so. But some of the conflicts are going to be external, such as the conflict between alpha 2 and alpha 3 and alpha 2 and alpha 4. Then these two have to talk to each other to make sure that, for instance, alpha 2 and alpha 3 are handled properly. So we are going to have a third layer which implements a solution to committee coordination. But the interface between this layer and the third layer are going to be fixed, depending upon the conflict resolution protocol or the committee coordination algorithm that we employ. So let me just show you three implementations. If we employ a centralized committee coordination algorithm or conflict resolution protocol, this is how it's going to look like. All the reservation requests are sent to this centralized component. So this is almost straightforward. This is an implementation based on a token ring implementation of committee coordination. So each component that has the token can resolve the conflict. For instance, this component can resolve the conflict between alpha 3 and alpha 2. And this can resolve the conflict between alpha 4 and alpha 2, and the same here. And the token is passed between these three components. Another implementation is based on dining philosophers. Each two conflicting interactions are handled by a common fork between two components that want to resolve a conflict. So then, as I said, the interfaces here is going to be constant. And then we can easily embed a committee coordination algorithm that we want to for implementation. In terms of correctness, what we have to show is that all these transformations that I talked about, starting from a high-level model such as this one up here, and then get this transformation, which has only point-to-point message passing, we have to prove somehow that this model behaves similarly to this model. So we were able to prove that this three-layer architecture preserves the semantics of the high-level model by showing the observational equivalence between the high-level model and our transformation. And by observational equivalence, I mean it's a bi-simulation. So I'm not going to go through the details of the proof. Now, in terms of implementation, obviously for a single engine, the implementation is easy. But when we want to go to distributed engines, then we have to take a partitioning scheme. And I'll show how partitioning scheme can change the performance of the generated code. Then there is also an input of a conflict resolution protocol. It can be centralized token ring, dining philosophers. These are the ones that we have implemented so far. And in terms of code generation, we now have implementation for TCP sockets, for MPI primitives and POSIX threads. So the POSIX threads implementation is ideal for a multi-core platform. So going back to our diffusing computation, I'm just going to show you the results of experiments. So these are the components that need to achieve a diffusing computation. These red and blue interactions show you the structure of the interaction. So this component is interacting with these 1, 2, 3, 4 components, and this is a multi-party rendezvous. Then there is the partitioning scheme, which basically means which interactions are handled by what interaction protocol components. This means that there is only one partition. This means there is two. This means that the second item here means that which committee coordination algorithm is employed. It can be a centralized one, token ring, or Dunning philosophers, or it can be nothing. That means it's a centralized implementation on just one machine. So let me directly go to this graph, which is interesting. The y-axis here is the total execution time of the generated code for a torus of 6x4 components, and these are different types of generated code. This is, for instance, 24 partitions implemented by Dunning philosophers committee coordination. This one is 24 partitions by centralized token ring, 4 partitions Dunning philosophers, and so on. So one trend that we can see is almost by increasing the number of partitions, we are increasing the level of concurrency, and we get better execution time in the generated code. The other thing is the totally centralized one, which means there is no concurrency, takes the maximum time. So this means that distribution is improving the performance. The other observation here is, which is very interesting, is the token ring implementation is performing better than Dunning philosophers. And this is a little bit counterintuitive because the Dunning philosophers implementation allows more concurrency, allows more parallelism, a higher level of parallelism. But it is not performing as good as the token ring one. The reason here is, although Dunning philosophers allows a higher level of parallelism, since there are more components that need to interact with each other to resolve conflicts, there is going to be more messages, and therefore there is going to be more overhead. Then we thought that this is a 6x6 torus. Let's increase the number of components, and that means if the local engines can work concurrently, with higher level of parallelism, maybe Dunning philosopher performs better than token ring, and that was indeed the case. So for a 20 by 20 torus, it takes 500 seconds to complete diffusing computation for Dunning philosophers implementation, and for the token ring implementation it takes about an hour. So I mean, this graph and the previous one clearly shows that different committee coordination problems, different partitioning, results in completely different performance. And that means that means several things. One is there is no silver bullet to generate code for a distributed implementation or a parallel implementation. And it also suggests that if we want to take this approach to generate code for distributed systems, we need to have a very rich library of different partitioning schemes and different implementations of committee coordination to get the best result.
But is there something wrong with centralized coordination?
Yes, I mean, in what sense?
And so in the three-layer approach, the middle layer could be a centralized coordinator.
Right. So Well, yes. One problem is if that component dies, then I mean the whole system gets stuck, right? I mean it's basically the question of distribution versus a central scheduler, and when there's only a central scheduler, that becomes a point of if it becomes a point of failure, then the whole system dies, right? Did I answer your question?
So in other approaches, part of the system would die or the whole system dies as well?
A part of the system. So, for instance, go back. Here. If this component dies, the system can still resolve the conflicts between alpha 1 and alpha 2, also alpha 2 and alpha 3. So interactions alpha 1, alpha 2, and alpha 3 can still take place. The only thing that would not take place is alpha 4, because this component would never authorize alpha 4 to be executed. So let me summarize the first part of the talk. The second part is going to be shorter. So we basically addressed a problem of generating distributed code or concurrent parallel code out of a high-level model where we have a set of components that are synchronized by a set of simple primitives. Each component then, after code generation, becomes a standalone application, and the synchronization primitives are meant to how the components work with each other. The implementation is in C++. We tried different transformations. We tried different committee coordination algorithms for implementing synchronization issues. These are some of the publications out of this work. So as you can see, the publications appear in distributed systems conferences such as DISC and SSS and IPDPS, and some of them are in the embedded systems conferences such as MSoft and SIES. Embedded systems conferences are interested in this work because it ensures correctness, which is good for safety critical systems. And for future work, there is a lot of things that we would like to do. For instance, we want to tailor our transformations for multi-core platforms, for shared memory platforms. Then we can leverage block-based or weight-free or transactional memory and all those types of implementations and solutions for to implement mutual exclusion. But for a distributed setting, there is still a lot of room to work on different types of schedulers, different types of committee coordination algorithms. I showed you three different solutions that we have not implemented. We have no idea yet how they are going to work in action. Another paradigm is to develop transformations for different type of applications. For instance, for peer-to-peer networks, for sensor networks, where energy is important, because it's not going to be all about execution time. In sensor networks, execution and computation is going to be cheap. What is expensive is radio, is communication. So then the question is how we can develop transformations that preserve energy as much as possible and possibly do more computation. There are questions on synthesizing the glue level or the interaction level, and another question is how we can leverage this framework to do compositional verification for instance, algorithms such as transactional memory and so on. So before I go to part 2, are there any Questions? Not really? Okay. So part 2 is about some work that I have been doing when I joined University of Waterloo. And that is on debugging and testing and tracing. And this is a joint work with Sebastian Fischmeister and Saman Nawab. The question that we are trying to address here is if we want to do debugging or tracing in a system, how we can minimize the probe effects on that system. Normally, we add instrumentation to a program. By instrumentation, I mean printf statements, breakpoints, and things like that. And this is not, in all cases desirable, because adding instrumentation means adding more probe effects. In time-sensitive systems, it means tampering with the deadlines. It means changing the overhead. It means basically manipulating the normal behavior of the program. So the question that we started asking ourselves was, how can we minimize these probe effects? So we came up with a notion of observability, and by which we mean that if we want to debug or test a program, we basically want to trace the value of a set of variables to evaluate a set of properties. For instance, if we want to evaluate whether A is greater than 100, I'm talking in a debugging and testing context, not in a verification context. Then that means we have to sort of record the value of A, the same thing for E and C here. And then the question is, of course, one way to do that is we add a printf here to add the value of A in a file or on the screen. But then the question is there any way to minimize this addition of printfs? So achieving observability in an ad hoc fashion can be done by traditional methods which tamper with the natural behavior of the program. And as I said, the examples are printfs and breakpoints. Now, in a concurrent setting, in a multi-threaded program, and in a real-time program, the outcome of this tampering with is going to be a little bit more amplified, because adding printfs and adding breakpoints is going to affect the context switches. It's going to affect the interleavings of threads and so on. So let's imagine we have these two threads. Don't worry about what the code is doing. This is just for an illustrative example. G is x plus y plus z, x plus z plus y. There is an if then else statement here, and 3 more assignments here. The value of C can depend on whether the if or the else branch is taken. And there is another thread which also defines the value of variable E. And variable E is shared between these two threads. So in an ad hoc manner, we have to add some instrumentation instructions to record the values of A, E, C, and E, and so on. And as I said, these addition of instrumentation instructions cause more interleaving scenarios, unpredictable context switches, changes in the timing behavior, in resource usage, and so on. So our goal is to reduce the deviation between the behavior of a given program and the program that is instrumented. So we have source code, and we have a list of desired variables that we want to monitor, or we want to log or debug. And our goal is to find a minimum number of variables that needs to be instrumented. So this is an optimization problem. Let me give you an extreme example of what I mean. And this extreme example is as follows. We have these 6 instructions which define the values of x, y, z, v, u, and w. X is q times 10, y is q divided by 10, z is q plus 10, q minus 10, q modulo 10, and to the power 10. All right? So if we want to debug the values of x, y, z, v, u, w, one possible way is to add a printf here after x, after y, z, and so on. Right? But perhaps a smarter way, this is what we call the set of variables of interest or desired variables. But probably a smarter way to do this is to only print f the value of q. And then we can extract the value of x, y, z, v, u, and w. Right? So by only adding one printf, we can extract the value of all these variables. This is what I meant by minimizing the instrumentation, the number of instrumentation instructions. So q would be the set of variables that have to be instrumented in order to observe the values of x, y, z, v, u, and w. And I call this an extreme example because the value of all these variables depend on only one variable, right? So this is our technical approach. We first extract the program slices of each variable of interest. Then we create something that we call observability graph, and then we check whether those variables of interests are observable using that graph. If yes, we try to minimize that instrumentation. If no, then we come up with a new instrumentation scheme. So this needs the notion of dependency between variables to extract slices. For instance, if we want to observe the value of A depends on the value of B, C, X, and E. So that means A depends on B in instruction L9. The same type of dependencies exist. And there can be chains of dependency. The other problem that is there is because we are doing static analysis here, statically we do not know if this if branch is taken or else. So we have to take both into account by static analysis. That means C can depend on F and G, and it can depend on D. So what we do is we take C, and then it depends on the instructions L3 and L5 at the same time. So dependency chain is basically a chain of dependencies where we start from the value of interest that we have, for instance A, and then we have to trace back all the dependencies to where the chain is complete. So one example of this chain is A depends on E, E depends on G, G depends on Z up here, right? And if we develop a complete dependency, then we should be able to always extract the value of a variable. In multi-threaded programs, it's going to be a little bit more complex because of existence of shared variables. So in this case, E is a shared variable between thread 2 and thread 1. So E is defined here in instruction L7 of thread 1, and it is also defined by instruction L1 of thread 2. So that means we have to take into account all possible interleavings. This can also depend on the memory models that we use. So I mean, the problem can be more complex. What we aimed here was basically sequential consistency. So to obtain the set of variables that define the value of a variable, we can use the notion of program slices. And there's a lot of work in the literature on slicing. And what we did basically was we took one of the algorithms for slicing concurrent programs, So for instance, to define the value of a, to extract the value of variable a, it's only sufficient to take these instructions into account, because the other instructions don't affect the value of a. Then when we have the slices, we construct this observability graph. So an observability graph is defined as follows. This is variable a. We call this a variable vertex, and this is a context vertex, which is the instruction. This instruction uses values of variables b, e, and c. And the same thing for x. E is defined by instructions either L1 or L7, which use variables s and g, and so on. We can complete the observability graph. And then having the graph, if we want to observe the value of a, then we have to find a coverage that covers the value of a. For instance, if I add instrumentation for variables d, f, y, and x, this is not going to be sufficient, because basically y and x are not sufficient to extract the value of g, right? And when we don't have g, that means we don't have c. We don't have c, then that means we don't have a. Now, if we want to observe the value of multiple variables, that means we have observability graph for multiple variables, and then that issue of minimization makes sense. All right, so the optimization problem that I was talking about is formally as follows. We have a concurrent program, a multi-threaded program. We have a set of variables v, which is the set of desired variables that we want to debug. And the question is, does there exist a subset of variables v prime, which is less than k, and k is the size of v, whose instrumentation makes all the variables in v observable? This problem, we showed that for sequential programs, not even for a multi-threaded program. This problem is NP-complete. For multi-threaded programs, we are going to have another exponential blow-up, and that is because extracting program slices for multi-threaded programs has another exponential blow-up. So we are suffering from two exponential blow-ups, one to solve our optimization problem, and the other one to generate the program slices. And this is the work that we used. It was published in ISTA, that we implemented to extract program slices. Our tool chain works as follows. We take a C program, a set of variables of interest. We implemented the slicer on their LLVM compiler. Then we give it to our observability checker. Our optimization problem is mapped into an SMT model, which we solve it by Yikes, and that shows where should be instrumented in the program. Let me show you the result of some experiments. So we aimed at studying two things. One was how much we can reduce instrumentation, and the second study was this reduction affects execution time of a program by what level. So our case studies were some popular concurrent data structures, such as concurrent linked lists and red-black trees. And we took different implementations. There is a lock-based implementation. There is a non-blocking implementation. The lock-based implementation is by Tim Harris. Actually, I think Tim Harris works for Microsoft Research in Cambridge. The obstruction-free or the non-blocking implementation is by Hagid Atiyah, and there is also a lock-free implementation, and there is also an implementation by transactional memory. So we took all these implementations to see how they behave when we instrument a set of variables in an ad hoc fashion, and when we instrument the variables optimally. So this is the reduction that we gained using our method. For linked list, which uses nested locks, the original instrumentation had 43 instructions, and the way we came up with this instrumentation for debugging was we took the third top variables that are defined in the program by the highest frequency, and we instrumented those. Any definition of those variable is the value of that variable is instrumented. Then we applied our method to find the minimum number of instrumentations that has to be done in order to extract the value of those variables. In the case of this nested lock, from 43 instrumentation instructions, we went down to 20. So that is pretty good. In some cases, it's less than 50%. In some cases, it's less. Some cases, it's more. In average, in the experiments that we conducted, we gained 45% reduction. So that was the effectiveness of our method. In terms of the effect on execution time, we conducted the following experiments. This graph shows the performance improvement factor, and this is the I/O delay of instrumentation. This is simulated. We didn't use different devices for instrumentation. So one of them was printf, the other one simulates printf, the other one simulates logging on an E2PROM, the other one on screen, the other one on disk. So these are different instrumentation schemes. So for instance, in case of linked list instrumentation, the obstruction-free algorithm by Hagedatiya, this shows the best improvement factor. So we took, in our experiment, 100 insertion operations in the red-black tree. And for different types of I/O delay for instrumentation, the improvement factor can go all the way to, in terms of execution time, all the way to 50 times. So we did the same type of work for sequential programs before we worked on multi-thread programs. We never reached this much improvement. I mean, 50% was something that I never thought, I never imagined. Sorry, not 50%, 50 times improvement. In some cases, the improvement is less than 10 times, and that is the case where the instrumentation was in a loop. When the instrumentation is in a loop and we cannot reduce it that much, then the improvement is not that much either. This graph shows the same improvement factor, but for different number of insertions. So we changed the number of insertions to red-black tree or to linked list from 200 to 1,000. And as you can see, in some cases, the improvement factor go all the way to 70. So that means that ad hoc instrumentation for debugging can slow down a program at least by 70 times in a concurrent setting. So the summary of this part of the talk is we looked at reducing the probe effect introduced by instrumentation instructions for debugging and testing purposes. And we tested our method for popular concurrent data structures such as linked lists and red-black trees. The problem is NP complete. That means there is still a lot of work to be done for designing heuristics. What we did was we transformed our problem to an SMT problem. But for large model, it's still going to be an intractable problem. In some cases, we showed up to 70 times gain in performance when we instrument a program using our method optimally. For future work, we are looking at designing heuristics. We are looking at the notion of observability in weak memory models. We are looking at optimization with respect to log size. It's not always the case that we want to, optimize. Sometimes for instance, in embedded systems, we have a device that only has, a certain size. And we can log things up to some extent. So we want to log things that makes the program as observable as possible. And we are looking at that probabilistic observability. That means, finding a set of variables that makes another set of variables observable by the highest probability. So thank you very much for your attention. I'll be happy to take questions.